Hey guys, what's up? Welcome back to the classroom. It's Mr. Low, and today we are going to move on to the next chapter, chapter 6, Work, Energy, and Power. Now, in this chapter, you can see very clearly there are three different concepts that we need to learn. Number one is what is work done and how to calculate it. Okay. Secondly, is the different types of energy. Specifically, we are going to learn what it means and how to calculate kinetic energy as well as gravitational potential energy, GPE and KE. And last but not least, what it means by power and how to calculate. Alright, so without further ado, let's get right into it. In section 1, we are going to talk about different types of energy and how to calculate kinetic energy as well as gravitational potential energy. Now this is the first part of the three-part video. Okay, I'm going to separate the whole chapter into three different parts. First part on energy, second part on work done, and the last part on energy. So this is the first part. Alright, so in this section we are going to learn what is the definition of energy. Okay, identify the various types of energy, and next, of course, what is the meaning of kinetic energy, what is the formula and how to use it, what is the meaning of gravitational potential energy, and as well as the formula and how to use it to solve problems. So remember, this table is like a checklist for you as you revise your work. After you revise and you come to line number 1, for example, are you able to recall the definition of energy? If you can, oh yes, great, then give yourself a tick, right? At the end of the revision, you should be able to achieve all this success criteria. That means you're good to go for exam. Alright, so let's carry on from here. Okay, part 1, energy. What on earth is energy? Okay, very often we say that, Cher or Dad, Mom, I have no energy to do any more work. Right, so tired, right? So from here you know that energy is required to do work. Without energy, you can't do work. So the definition is exactly like this. Energy is the capacity to do work, right? Capacity, if I were to use another English word to rephrase, is like the ability, okay, ability of something, an object, okay, to do work. Right? So energy has the SI units of joules, capital J. Right? And energy, of course, is a scalar quantity. Let's recap. What is the difference between scalar, and vector? Right? VECTOR. Right? So for scalar, you don't need the direction, but for vector, you need to give me the direction. Clearly, energy is a scalar quantity because it does not make sense for you to indicate a direction. Okay, but of course, when it comes to layman terms, any Tom, Dick, and Harry, when they talk about energy, there can be many meanings to the word energy. It can be the energy that we get from sleeping, right? Or after taking a nap. Oh, I just took a nap. Now I have energy. we don't refer to that in physics. There are also many mysterious forms of energy like chi, this kind of a voodoo mojo kind of energy. We are not interested. We can't calculate them. That's not science, right? But of course, in physics, in science, there are many different types of energy, and this table sums it up. Okay, so there are many types here. In this chapter, we are mainly interested in calculating GPE as well as KE, right? But of course, you need to commit to memory all these things except for nuclear energy. What it means by all this energy, for instance, what's the meaning of chemical potential energy? These are the so-called descriptions. You must know all this except for nuclear energy. Alright, so first type of energy we're interested in calculating, kinetic energy. I think this is something that we already know, right, from our primary school, that anything that's moving has kinetic energy, right? So kinetic energy is the energy possessed by moving objects. Okay, so the definition is here very clearly, is the energy of a body possesses energy is the energy that a body possesses due to its motion. So long as it's moving, then it has kinetic energy. And the formula is half times m times v square, where m is the mass of the object. And remember, we must always work in SI units. Okay, so everything in SI units, and v is the speed of velocity in meter per second squared. All this in SI units. All right, so take note of the square here. Okay, so next thing is, yeah, we already know that any moving object has a speed of velocity, therefore possesses ke. But any object that is not moving has speed equals to 0, and therefore ke equals to 0. Okay, you can see very clearly from the formula itself. If I were to substitute v equals to 0 into the formula, the ke will naturally be 0. Alright, so let's try two very simple examples over here. The first one is already given to you. How do you use the formula? Alright, so first thing, if I want you to calculate the kinetic energy, of any moving object, I must first give you the mass. So m equals to 10 kg, and must also give you the speed, or v equals to 5 meter per second. All you have to do is substitute into the formula. First thing first, remember, quote the formula. Okay, this is very important here. I keep emphasizing this in class, right? Remember to quote the formula first and substitute in the correct number, and you should get the correct answer. Alright, now next one. This one we already know. This object is not moving. Speed equals to 0. Well, the m is 10. So what is the kinetic energy of this object here? Alright, so you don't need to calculate actually. You know that it's 0, alright, but let's just work out the math to prove that it's indeed 0. Again, quote the formula. K equals to half mv squared. Let's substitute in the correct numbers. Mass is 10 kg. Alright, check that the unit is kg, yeah? And the speed, v is 0. 0 square, 0. The whole thing is 0 joules. Right, so very clearly, anything that's not moving will have kinetic energy of 0, or rather no kinetic energy. Right, so this is a very straightforward calculation. I give you the mass, I give you the velocity or speed, you tell me the kinetic energy. Now, there's another type of question that is not in this note, beg your pardon. Can you please flip back to page 2 and take down this type of question, right? This type of question involves you to calculate backwards, okay? So, this kind of question will go something along this line. Okay, an object. You might want to take down the question as well. Has mass of, let's say, 10 kilograms. Pardon me, 10 kilograms. And kinetic energy of, let's say, 640 joules. Okay, so clearly this object here is moving. It has a mass of 10 kg and has a kinetic energy of 640 joules. Clearly the question will ask you, what is the speed? What is the speed of the object? Alright, so what is the speed of the object? So this is your focus. Alright, so let's answer the question as you usually would. First, quote the formula, right? K equals to half mv squared. And in this case, instead of calculating Ke, we are interested in calculating V. So let's substitute all the values in first. Okay, so Ke is 640 joules equals to half times mass is 10, and then v squared. We don't know what is v. Alright, so let's simplify the equation a little simpler. So from here we can divide 5 over by both sides, and we have v squared equals to 640 over 5. That gives you 128. Okay, so v squared is 128. Yeah, that's right. Is that all to the question? Of course not. because this is v square, not v. We are interested in finding v, right? So how do we have v square, how do we find v? We take the square root, that's right, okay? So we just simply take the square root and you should have the answer. Okay, I'm not going to press the calculator, or maybe I should. Give me a while. So at home you can do it with me. What is the value of square root of 128? It's approximately 11.3. It's approximately 11.3 meter per second. Okay, final answers to 3 significant figures. Alright, so this type of question, just take note, you need to take the square root, reverse engineer to find the speed of the object. And we're done with kinetic energy. Here's the next part, gravitational potential energy. This is also something we're familiar with. Okay, any object that is at a height above ground should have gravitational potential energy. Alright, so for instance, you're holding a basketball at waist height, right, or at chest level. That basketball has it's at a position at a height above ground, and therefore it possesses GPE. So definition here again, GPE is the energy that a body possesses due to its position. When we say position, we mean, for instance, we actually mean the height above ground, right? So this basketball here has is at a height above ground. Due to its position, it now has GPE. Alright, so let's take a look. The formula, GP equals to m times g times h. Again, we come to see this g again, right? If you do remember, g is the gravitational field strength, okay? And recall, g is about 10 Newton per kg on Earth. Near the surface of the Earth, of course. If you start to move away, from the Earth into space, then g will change, right? But we're not interested in that. Okay, m is the mass and h is the height above ground. Do take note that you have to work in SI units, so everything in SI units, meters in this case. Okay, so mass times g times height. Of course, you can imagine, right? The bigger the mass, the heavier the object is, the more gravitational potential energy it has. The higher it is above ground, it has more gravitational potential energy. So let's take a look here, a simple example here. Again, another object of mass 10 kg, m equals 10 kg, with the height of 5 above ground. Calculate the gravitational potential energy. Alright, so first thing, again, we must put the formula mgh, and now let's substitute in the correct numbers. M is 10 times, g is also 10, and height in this case is 5.0, and you get the answer of 500 joules. Alright, so an object of mass 10 kg at a height of 5 meters above ground should have a GPE of 500 joules. Next, how about this? What do you think? So you see that the object is exactly lying on the ground. Is there a height above ground? The answer is no, clearly. So by right, without calculating, you should already know that GPE is 0. But let's just do the math. Okay, let's just do the math to convince ourselves. Again, GP equals to mgh. Mass is 10, g is 10, but height in this case is 0. And as a result, it does not have any GPE. Alright, so again, just like the different types of questions for kinetic energy just now, sometimes we might give you the GPE and ask you for the height above ground, or ask you for the mass of the object. Okay, so you need to know how to do your algebra, how to manipulate your equation to make something the subject, right? For instance, if I ask you for the height, then you must be able to make height the subject. Okay, so I think that's quite simple. So these are the two types of energy that we need to know how to calculate. First, KE, half mv squared, and then GPE, mgh. That's it. Okay, moving on, we have a very important concept here called the conservation of energy. Okay, So in this section, you will recall the meaning, or rather the principle of conservation of energy is like a definition, and you're going to apply this concept here, this principle, to solve questions. All right, so let's quickly move on. The key question here is, can we create energy out of nowhere? Clearly not. Okay, this is not in the comics or any movies. We can't just make fire out of nothing. You know that if I want to start a fire, I must have the fuel, right? I must have the fire, the heat energy to start the fire first. And the fuel contains the chemical potential energy, to start the heat energy from the fire, right? So we can't make energy out of nowhere. Neither can we make energy disappear into nowhere. All right. So this concept is called the principle of conservation of energy. It's very, very famous. All right. So the whole principle is very long. Okay, there are two parts to it that you need to remember. Now, you might have come across this in lower secondary science. In lower secondary science, we only taught you the very first part here, which is this, right? Principle of conservation energy states that energy cannot be created nor destroyed, okay, but can be converted from one form to another. This here is part 1. This you might have already encountered or recalled. The second part here you also need to know is that the total energy in an isolated system remains constant. What does it mean by isolated system? This thing means, here it's stated over here. What does isolated system means? It means that the system does not interact with the surroundings or does not exchange energy with the surrounding. Okay, what do I mean by that? So let's say you have an object on the table. It's just sitting there, not interacting with any other things. Now this object here is now an isolated system. But if someone comes in and exert the force and push this object, and now is interacting with something else, this object now is no longer isolated. Okay, you get the idea? All right. So let's come back right here to the principle of conservation. Right, energy cannot be created nor destroyed, but can be converted from one form to another. You know that, right? Energy can be converted. The food that you eat, that you had for breakfast this morning, if you don't have the habit of having breakfast, please do, right? The breakfast that you have for this morning contains, possesses chemical potential energy. Let's go back to the different types of energy here and take a look. Chemical potential energy. Energy stored in fuels, petrol, or food, etc. Right? So the food that you had for this morning for breakfast contains chemical potential energy, which after digestion, respiration, all the biology stuff, it becomes energy for you to work, like your kinetic energy or the heat energy that's given off from your body because you have a temperature, right? Okay, so yeah, the total energy in an isolated system remains constant. So when we ask for the principle of conservation of energy, you need to give me both the parts. I hope it's clear enough. Okay, so moving on. Yeah, so let's look at, of course, we're not just looking at kinetic energy and gravitational potential energy. This principle of conservation of energy applies to any type of energy. Just like what I said just now, the food that you consume contains chemical potential energy. So here in this example, you have a light bulb and the input electrical energy is 200 joules, right? So you connect the wires to a battery, you connect the wire and to a battery, so-called, right? Okay, like this, okay? And the input electrical energy is 200 joules and it gives out light energy of 150 joules. Now also, sometimes you might realize that if you put your hand near light bulb, any light bulb, you might feel some heat coming out from the light bulb. That's heat energy, right? So how much heat energy is given out by the light bulb if we know that the light energy is 150 joules? Okay, now this one I think you already know. 150 plus this amount should give me 200 joules, right? So this actually, if you already know this is actually conservation of energy. Energy cannot be created nor destroyed, right? So how much energy I put in, 200 joules, should come out should come out as 150 plus 50. No energy should be gone, right? It's just a matter of being converted from electrical to light energy and heat energy. So the conservation here is electrical to light and heat, right? Plus heat, right? And the total amount of energy of this light and heat should be exactly equal to the amount of electrical energy that you put in. So very simply, 200 minus 150, 50 joules. No energy is added, no energy has disappeared, right? Very simply. Now, so we come to conservation of energy or conversion of energy between GPE and KE. Okay, and the story goes like this, right? You have a ball that is sitting at a height above ground. It possesses GPE of 500 joules. Okay, now it's released to allow it to freely fall in under gravity, and let's say it's at a height of half h. That means it has dropped halfway down to the ground. How much GPE and how much KE is there now? That is the question. Okay, now you don't know the mass of the object, you don't know what is the height of the object. So how do we know how much GPE is there? Well, if you're sharp enough, you realize that, oh, the ball lost half its height, its original height position. So that means the gravitational potential energy should be halved. It should be half, right? So GPE equals to half of 500 originally. That gives me 250 joules, right? So at this position, half h above ground, just now it was at, height h above ground. So its GPE is halved, 250 joules. So how much KE do we have now then? Alright, so if you're sharp again, you would think of at the start, what was the total energy? That is the concept here. What is the total energy that we had, or rather the ball had at the start? Okay, so you need to go and calculate the total energy, which is just this sum of these two. That gives me 500 joules. Alright, now by the conservation of energy, this total energy 500 joules should not change. That means if when the ball is at half height from the ground, the total energy should still be 500 joules. Okay, no change. This is the key here, right? So from there we know that the amount of kinetic energy is nothing but 250 joules. Okay, I hope this is clear enough. The total energy does not change. That is the conservation of energy. Alright, now at stage 3, it is near the ground, it's still moving just before it hits the ground. Just before it hits the ground, right? What is the GPE and what is the KE over here? Alright, now from previous example, when we calculated the GPE for an object that is near the ground, or at least just about to hit the ground or near the ground, we know that it is no height above the ground, right? The GPE is 0. So back to this case, the ball is just about to hit the ground, not exactly, right? So we don't talk about bouncing yet. The GPE is 0 joules because it has no height above the ground. This is very easy. So what is the KE now? How much KE does this ball possess? This one you should know. The answer is 500 joules. Why? Because again, back to the same thing, total energy is 500 joules. The total energy does not change at any of the 3 stages. This is the conservation of energy. Alright, of course, in reality, this is not true because there is air resistance. So there is actually energy loss to air resistance that is dissipated off in terms of heat. Okay, but of course, for exam purposes, everything is simplified. We assume no air resistance. Okay, so notice how the total energy GP plus K remains the same throughout the fall. This means that the total energy in an isolated system remains constant, 500 joules in this case. Okay, now we can also apply the same thing to a pendulum. So remember, a pendulum swings from the top to the center position, back to the other side, and then back to the top again. That's one oscillation, yeah? Okay, so the GPE at W, so is equals to the Ke at Y. Why is that so? Because as the ball, or rather the pendulum bob, swings from W to Y, can you see that it is actually losing height? So let's say this height here is H, right? Originally, this bob here has some GPE and no Ke, right? It has some GPE and no Ke because, well, it's at the top point, it's not moving. When it swings down to the lower point Y here, you can see that the speed increases, but it loses height. So you can see that some GPE, okay, some GPE converted into Ke, right? Just like the case of the ball previously, right? The GPE is being converted into kinetic energy. Then, as it swings back up again, same story, the kinetic energy is converted into GPE. And then over here, it is fully GPE again. In the absence of air resistance, you know that this height will be the same, right? The amount of GPE here should be equal to the amount of GPE here. Okay, but yeah, in the case where there is air resistance, you see that the height gets lower and lower. I think you have experience with that. Okay, so let's look at one example here, a worked example. An object of mass 5 kg is dropped from a height of 2 meters above ground. So with these two information, I can already calculate the GPE at the start, right? I can already calculate the GPE at the start. Assuming no air resistance, calculate the Ke of the object just before it hits the ground. Okay, so this is the same case as just now. You have height of 2 meters and the mass is 5 kg. And the mass here is 5 kg. What is the Ke here just before it hits the ground? Right? So presentation of your answer is very important. By conservation of energy, the GP at the top equals to Ke just before it hits the ground. This is this case, right? You can see here, because of conservation of energy, the GP here equals to the Ke over here. All the GP has been converted into Ke just before it hits the ground. Yeah. So we go ahead and calculate the GPE first to be 100 joules. Right, remember, of course, I keep nagging at you, remember to quote the formula. So therefore, by conservation of energy, the Ke just before it hits the ground is 100 joules. So simple. No energy is lost, no energy is gained. In this case, total energy is the same. All right. So an object, next example, an object of mass 4 kg is dropped from a height of 4 meters above ground. It's a very simple, similar concept, similar question. Again, you can straight away calculate the GPE. Calculate the velocity. Now we ask for the speed. Now there's one extra step here, because just now we asked for Ke. Now we ask for the velocity of the object. Okay? But here the concept is still the same. Let's draw the same diagram. In this case, the height here is 4 meters. The mass here is 4 kg. Right? So we ask for what is the speed. But you know that we can't directly calculate. Actually, we can directly calculate the speed by considering the acceleration. I will show you the second way of working this question, right? So, but we know that this velocity is related to Ke, half mv squared. That is something we can calculate by conservation of energy, right? So let's do this together. So the first line that you must quote, by the conservation of energy, okay, so by the conservation of energy, GPE at the top equals to kinetic energy of the ball just near the ground. just before it hits the ground. Yeah. Okay. So we can go ahead and calculate the GPE just like the example previously. So GPE equals to mgh. Mass is 4, g is 10, g is 10 over here, and height is 4. That gives me 160 joules. So by conservation of energy, we know that Ke near the ground is exactly equals to 160 joules. But we're not done yet because we are told to calculate the velocity. So let me just write here. I hope you have some space. Right. So we are tasked to find the velocity, and we know that Ke equals to half mv squared. This is what we are interested in over here. We know the Ke, 160 joules. We know the mass, that is 4. So we are going to calculate the v squared, right? So v squared is nothing but 160 over 2. That gives me 80. So the velocity is square root of 80. Which, let me summon my calculator again. Square root of 80, and that gives me 8.94 approximately. Approximately 8.94 meter per second. That is the SI unit for speed or velocity. Okay, so take a pause here in the video if you need to take down the answer. Okay, I'm just gonna very quickly tell you what is another way to calculate this question. No, sorry, you don't have the relevant formula, my bad. Okay, so this is just the only way that you can do it. Okay, calculate, find the speed by looking at the energy changes. Alright, so that's it for this part of the video. Okay, in this video we have learned a couple of concepts here. Okay, what is energy? The capacity to do work. Okay, we also need to know the different types of energy and what it means. We learned that what is the meaning of kinetic energy, its formula, how to apply the formula to, to find the Ke of any moving object, or find the velocity of an object given its Ke. Right? We also learned about the second type of energy here, gravitational potential energy. Okay, that is possessed by any object due to its height above the ground. We know the formula mgh. We applied to calculate the GPE of some object, and we learned a big idea here, which is the conservation of energy. Okay, remember that there are two parts to this thing, yeah. Okay, the total energy in an isolated system is always constant, and we see it in this case over here. The total energy in an isolated system is always constant. Okay, so with this idea, we can then calculate, what is the kinetic energy of an object that is dropped from a height just before it hits the ground? Or I can even ask you, what is the kinetic energy of the object at some height above the ground? If I give you the height, you should be able to calculate the kinetic energy for me, right? So once we know the kinetic energy of the object just before it hits the ground, you can then go ahead and calculate the speed just before it hits the ground. Typical questions will sound like this. Okay, so in the next topic, next section of the chapter, we are going to look into work done. Okay, so I hope you enjoyed this video and learned something. I'll see you in the next video. Take care.